Hello, everyone. Today we're going to go over Unit 6, which focuses on acids, bases, and acid and base reactions. What we will do first, we are going to look into properties and characteristics of acids and how to classify and categorize acids. We will look into the nomenclatures of acids and how we can construct names by looking at the molecular formula of specific acids. Once we finish with acids, we will discuss bases and how look into and how to classify bases, and also how to um, look into the properties and characteristics of bases. Once we finish with acids and bases, we will examine property. We will examine the reactivity of acids and bases, or what's also known as a neutralization reaction. And then we will finish up the unit with learning some alternative definitions for acids and bases. So let's get going and look into the characteristics of acids. And probably one of the first properties of acids that we are pretty much all familiar with is that acids are known for their sour taste, right? So we all add some sort of vinegar or some sort of salad dressing to our food in general and to our salads, and we do taste that tangy sour taste that comes from the addition of acid. So the sour taste is the first thing that pretty much we all as scientists probably learned about acids. The second thing that the second property that we know the second property for acids is the fact that acid will turn the litmus paper color from blue to red. So if you have a litmus paper and you submerge that into a solution that has acid, you will see the color will change from blue to red. And that's probably one of the early tests when it comes to determining pH of solutions using the litmus paper. So we'll change the color from blue to red. The last property for acids that we have here is that acids will react with base to form salts, and that basically applies for bases as well. So if you have a okay, let's do this. So if you have NaOH plus HCl, so this is the base, this is the acid, will form NaCl plus water. Will form salt plus H2O. So acids will always react with a base to form a salt. And the same rule basically applies for the base. The base react with the acid to form a salt. And that's another property of acid. It actually not only forms a salt, but also forms water. And that's basically the generic reaction, formula for base and acids. So three properties for acid, just to wrap it up. The sour taste. The second thing we have that the litmus paper color will change from blue to red, indicating this is an acidic solution. And then the second thing we have is that acids react with bases to form salts. When it comes to definitions of acids, so how do we define this substance is actually an acid? A scientist called Arrhenius, which is one of the Nobel Prize winners in chemistry, he defines acids as a substance that generate hydronium ion in solution with water. So if you were to add water to a solution to an acid, the acid will dissociate and form hydronium ions. So one of the really common acids that we have is HCl, which is also used in it's used in as a food additive. It's also used to clean any impurities of metals because such a really strong corrosive acid. HCl, if you react that with water or you add it to water, you will have protons formed plus chlorine ions formed. So this is what we refer to as the hydronium ion, the proton. Now the reason why do we call it a proton? Because as you know, hydrogen atom, a stable hydrogen atom, would have one electron and have one proton. When we say a hydrogen cation, which means that we lost the electron here. So that means it's plus with one proton left. Oops. So this hydrogen cation only has a proton within its configuration. So that's why we refer to it as a proton, because it's basically just a single positive charge hanging around. Okay, so this hydronium is not really stable. So what happens? This proton, I'm sorry, so I don't want you to confuse this one. We don't call this a hydronium. The hydronium is the H3O, which I'll explain in a second why, how it forms. So the proton is really an unstable positive particle in the solution. So what happens, as we all know, H2O, it has plenty of negative charge to satisfy this positive charge then here, okay? Because if you remember, this one is partially negative, this one is partially positive, this one is partially positive. So this positive charge that I have here on the proton, it will eventually start forming a bond with the electrons, with the non-bonding electrons over the oxygen and the water molecule. So eventually what happens, this water molecule would look like this. You have hydrogen, you have hydrogen, you have hydrogen, you have two non-bonding pair if you have a positive charge in here. Okay, so we call this hydronium. This is the hydronium ion. Okay, so an acidic solution, again, it's a solution that has a large amount or has a significant concentration of H3O ions, and that's what we call it, acidic solution. So any substance that forms a proton or forms a hydronium, according to Arrhenius, we call that material or we call that substance as an acid. Okay? We categorize acids based on their type, on their strength, or the number of acidic protons, because some acids will have more than one proton that are willing to donate and willing to dissociate in a solution of water. Strength, some acids are strong acids, other are weak acids. Something like HCl, it is considered really one of the top, on the top ranking strong acids. Other acids, something like acetate, for example, which we will look at in a second, that's considered a weak acid. Before we look into strength and also the number of proton generated, let's look first into types of acids. First thing we have here is the binary acids, which have the general formula of HX. So something like hydrogen fluoride would be considered a binary acid. Hydrogen chloride would be considered a binary acid as well. HBr, HI, so on and so forth. X in general here is a halogen. Okay, when we say it's a halogen, if you look at the periodic table again one more time, it's the group that it's right next to the noble gases to the far right on the periodic table. Okay, so those guys, they always form binary acids. And also, when we say binary, that means it has a single proton that it's willing to dissociate. Binary means a single. That's why it's also called a binary acid. The next thing that we have here, and among this group of acids right here, HCl is the strong acid. Okay? Everything else is a weak acid. The next type of acids that we have here is the oxyacids, which has the general formula of HA, XB, OC. Now, A, B, and C, those are subscripts, which means those are numbers. So if you look at something like H2SO4, this is A, this is B, and this is C. So an oxyacid would have a formula of HX. Oh, so X could be any element from the periodic table. Okay, that's how you can really identify the oxyacid. So if you look at a molecular formula for an acid and you see there is a hydrogen, there is oxygen, there is another element from the periodic table, You would call that one as an oxyacid. Something like acetate or acetic acid, I should say, which is CH3 COOH, which we're going to look at in a second here. So this one here also has hydrogen, has oxygen, it has carbon from the periodic table. So it has three elements which somewhat meets the criteria of an oxyacid. But in this case, we actually call this one organic acid because it has carbon and it has hydrogen. Okay, so it is a hydrocarbon basically with oxygen. So we refer to the acetic acid as a hydrocarbon. We refer to it as organic acid because of the hydrocarbon structure of the acetic acid. Okay. Now, what you are looking here, this is essentially the same compound as the way that I wrote it down here. Is just it's this molecular formula has been restructured to indicate the acidic hydrogen. Okay, because as you see here, there are three more hydrogen that are really not involved in the dissociation reaction to form the hydronium ions. So the acidic hydrogen is often written in a way to indicate that this is a different hydrogen than the other hydrogens in the molecular formula. Okay, and I believe we'll talk about this as we get close to the end of the acid part of this unit. Okay. So that's when it comes to types of acids. Next, we can classify them based on their strength. So we have strong acid and we have a weak acid. So a strong acid, that means you have a really high concentration of hydronium ions. One of the really common strong acids is HCl, which is used in food processing. It's also used to treat metals with any impurities involved because it's very corrosive and it's very strong. So if you were to react hydrogen chloride with water or dissolve it in water, what you will get hydronium ions or protons plus Cl minus or chloride anions. Okay. So when we say complete dissociation, that if I were, for example, if I were able to count 10 molecules of hydrogen chloride added to water, what I will get in my products, a complete dissociation of the hydrogen chloride, which would result in 10 counts of protons plus 10 counts of chloride, okay, anions. So that's a complete dissociation. So at the end of my reaction, what happens, there is zero HCl, everything is gone, and everything at that point had turned into 10 and 10, had turned into chloride and and a proton and hydrogen proton, or also you can write it as H3O. Okay, so that's why we call it a very strong acid. The weak acid, on the other hand, there is a reversible reaction that takes place with water that really generates the acid and generate more acid backward. So as we see here, there's one this reaction is going from left to right. So it's a complete dissociation reaction. There is no reversible reaction taking place in this case due to the strong acid nature of the hydrogen chloride. In an event when you have a weak acid, something like acetic acid in water, what you will get acetate plus H3O. Okay? But because this is a very weak acid, the number of hydronium protons, hydronium ions, is very small. So let's say, for example, that I've added 10 counts or 10 molecules of acetic acid. My reaction at the end, I would still have 9 acetic acid that did not really dissociate and you have 1 acetate and you have 1 hydronium ion. It's not only that, with a weak acid, there is a reversible reaction that actually goes from the products to the reactant. And because of the acetate is such an unstable molecular structure, what happens, it turns back and it takes the proton of the hydronium ion. Remember this one with a positive charge. Because of the acetate has a very weak, it's very unstable. It basically takes this proton back, um, and it reverses reaction into the formation of the acetic acid one more time. So the concentration of the hydroniums remains extremely low. That's why we call it a weak acid. So a weak acid is due to a reversible reaction with water generates significantly less hydronium ion of each molecule of acid added to water. Okay? So that's another way to categorize acids, which is strong acid and weak acid. Um, so let's look at this diagram here. So when HCl dissolves in water, as you see here, will form chlorine and hydronium ion. Okay? So this proton here will bond to water and form the hydronium ion. It's a complete dissociation, as I said early. At some point of this reaction, there will be no HCl, and it will be all Cl and all hydronium ion. Okay? When it comes, if we put this in context of count, so if you start with 250 chloride, hydrogen chloride, for example, molecules of hydrogen chloride, at the end of the reaction, you will have 250 hydronium ion, 250 chloride ions, and you'll have zero HCl hydrogen chloride molecules because all the hydrogen chloride had dissociated into protons and chloride ions. Okay. So a solution of strong acid, as you see here, you have the hydronium surrounded by the negatively charged oxygen end of the water molecule. And we have explained that and why this happens this way due to the partial positive charge and partial negative charge that exists over the water molecule. And you have the chloride ion surrounded by the positively charged hydrogen end of water. And that's the only way to stabilize this this bond, right? Because of the partial negative charge, partial positive charge over the hydrogen side of the water molecule. Okay. When it comes to weak acid and water, a dissociation also takes place. In other words, we still form the hydronium, ion. But what's happening, the number of the hydronium ions that is getting generated, it's very small compared to what happens when it's a strong acid. So, for example, if we're looking for acetic acid here in this case, the hydronium ion is getting generated, and the acetate also is part of our products. Now, what we notice here also in terms of weak acids, we see these two double-sided arrows, which indicate there is a reversible reaction that goes from the products back to the reactants. And that's simply because the stability of the acetate is very low. So what happens, the acetate will take back the proton from the hydronium, resulting in water and resulting in the acetic acid one more time. So in an event when we have an acetic acid solution in water, what happens, we have a very low concentration or a very low count of hydronium ions, which contribute to the fact that this is a weak acid, and we still have the acetic acid molecule it's pretty much just intact, and the proton has not left. And again, and that's because it's a weak acid, and that's because of the acetate is a very unstable structure. Okay. If you do that in numbers, you have the acetic acid, 250 molecules of acetic acid, and due to the reversible reaction, you'll have only one hydronium ion, and you'll have only one acetate ion because it's very not stable, and the acetic acid remains the predominant content of the solution with a very low concentration of the hydronium ion. Okay, which means it's a weak acid. How does that look in a flask? So you will see the hydronium ion surrounded by the negative charge of the oxygen for the water molecule. Okay, and you have the acetate surrounded by the positively charged hydrogen end of the water molecule. In a typical acetic acid solution, there is about 250 times as many uncharged acetic acid molecules as acetate, and also hydronium ions. So the concentration of hydronium ion is extremely low, which if you were to put a pH or a stimulus or a limit or a limit litmus paper, for example, the acidity will be very, very low. Now, acid is also identified based on the number of protons. So, for example, we have monoprotic acids, which means the acid that basically have only a single proton within its structure, and the polyprotic acids, and those are the acid that has or includes multiple protons within its structure. So something like a monoprotic acid, all the binary acids. So like HCl, for example, is considered a a monoprotic acid. And the reason why, because there is only a single hydrogen atom here. So there is only a single proton is getting generated. So a monoprotic acid, each molecule of an acid can donate one hydrogen ion. When it comes to polyprotic, it could be either a diprotic acid, something like H2SO4. The reason why it's a di, because I have two hydrogen ions that can potentially be lost. Acidic hydrogens, or the triprotic acid. Triprotic acid, something like H3, the phosphoric acid, H3PO4. And again, it's tri because I have three hydrogens that I can potentially lose at three different dissociation steps. And we will look at the dissociation of the diprotic and triprotic acids shortly. Okay, so acetic acid, for example, it has different way when it comes to writing the molecular formula. We can either write it as HC2H3O2, CH3CO2H, or CH3COOH. Okay, now these are all the same empirical formula, especially when it comes to counting your how many carbons, hydrogen, or oxygens you have. So it's the same compound, it's just written differently. Okay, now as you see here, there's four different hydrogens in the acetic acid, but not all four are participating in the deprotonation process and by donating that hydrogen, acidic hydrogen. So that's why we call one of those hydrogen as the acidic hydrogen. The other three hydrogens are not involved at all with the acid properties of the acetic acid. So that's why in some cases and in some books you will see the acetic acid written this way to indicate that this hydrogen right here, this is the acidic hydrogen. I personally like to write it this way because this one also indicates the acidic hydrogen. Okay? The other hydrogens that you have in here, which is the hydrogen that are bonded to the carbon, those are not involved with the it has nothing to do with the acidic properties of the acetic acid. Okay? Sulfuric acid is considered a strong diprotic acid. Each H2SO4 molecule loses its first hydrogen ion completely. That's why H2SO4 is classified as strong acid. So classifying as strong acid is based on the dissociation, and how the how the hydrogen ion is lost. If it is completely dissociated and is completely donated, then we consider that as strong acid, as we talked about it earlier. So the H2SO4 is a diprotic, right? Because H2SO4 has two protons and has two hydrogens, I should say, to donate. So the first dissociation happens completely without any reversible reaction. Okay, the arrow points only one side from the reactants to the product. That's why it's considered a strong acid. Okay. On the other hand, the second proton that comes out from the HSO4 and the second deprotonation reaction, which is this one right here, this proton will be considered, or this proton dissociation will be considered a weak acid. And that's because this the sulfate anion right here, this polyatomic anion, it's very unstable and will eventually grab the proton from the HO3 and reverse the reaction back toward the reactants, to the reactant side of the equation. Okay, so that's why this second proton here, this is considered weak, a weak acid. Okay. So it could be an indication for you to tell if it is a weak acid or a strong acid reaction. If it is a strong acid reaction with a complete dissociation or complete deprotonation, you will have only one arrow pointing from the reactants to the product side. While in a weak acid dissociation or deprotonation, you will have two arrows pointing toward the reactants and toward the product, which means there is a reversible reaction happening simultaneously with this with the primary reaction. Okay. Um, there is also another acids that has multiple protons that goes through multiple stages of deprotonation. Example for that one is the H3PO4, the phosphoric acid. So this one is considered a polyprotic acid. Okay, and polyprotic should be a one word, by the way. So when I say polyprotic acid, that means there is three protons that this acid molecule is willing to basically donate and let go. The first dissociation or the first deprotonation process, you have H3O, PO4. Oops, we forgot the water. Oopsie. Plus H2O, and that will give H2PO4 negative. Remember, every time you take a proton from the H3PO4, you're taking a positive charge. As a result, you will have a deficit of a positive charge. Then you will have a negative start showing up here. Okay? Remember, the PO4 is a 3 negative charge, but because we have the H3 positive, the 3 negative with the 3 positive will cancel out. That's why you have H3PO4 with a net charge of 0, or it's neutral molecule. But every time you take one proton, you're basically destabilizing the charge, or the charge is no longer balanced. So you'll have more negative charge than a positive charge. Okay, so that's why you will have H2PO4 with a negative charge showing up here, plus the hydrogen proton, or the proton that we just got dissociated from the H3PO4. So now if we go to the second stage of the deprotonation process, H2PO4 with a negative charge plus H2O. And in this case, we will have a reversible reaction because the second proton that comes out always behave as a weak acid. So always keep that in mind. So H2PO4 with losing a proton, HPO4 with 2 negative charge at this point because we lost 2 protons. And this one is an H plus. Okay? So this is number 1. This is number 2. Number 3, the last deprotonation reaction, which is HPO4 negative 2 plus H2O. This one is also a weak proton deprotonation. This one will be PO4 3 negative plus H positive. So overall, through the 3 steps of the dissociation of the proton, we have lost 3 protons at 3 different reactions. The first one was a strong acid. The next 2 are weak acid due to the reversible reaction. Okay, for the same reasons that we mentioned before. So that's when it comes to polyprotic or diprotic acids that contains more than one proton that it's willing to donate, or acidic protons, which goes through multiple dissociation reactions like the H2SO4 and like the H3PO4. Okay. 2 things that I would like to really highlight here to pay attention to. Every time you go through a dissociation reaction and losing a proton, make sure that you're displaying and calculating the correct charge over the polyatomic ions, like the negative here and the -2 and the -3. When it comes to the second and third deprotonation, make sure to use the reversible arrows to indicate a reversible reaction and also a weak acid behavior. Okay. So let's sum up everything in terms of Arrhenius acids. So we talked about binary acids, we talked about oxyacids, and we talked about organic acids. In the meantime, we also classify them as strong and as weak acids. When it comes to strong acids, as I mentioned earlier, these are the acids that you need to worry about when it comes to strong acids. So, in the exam, I may ask if this acid is strong acid or weak acid based on Arrhenius definition of acids. If it belongs to the group of hydrogen chloride or nitric acid or sulfuric acid, then it's a strong acid. Otherwise, it's a weak acid. Okay. So for binary acids, we have the HCl, which is also considered strong acid, or we have also the hydrofluoric acid, also a binary acid, but it is considered a weak acid. Okay, the reason why we call it a binary because you have only a single hydrogen here to lose and behave as an acid. Okay, the oxyacids, that's the one with the formula, with the general formula of HAXBOC, right? So HNO3 will be part of this oxyacid group, H2SO4, H3PO4, so on and so forth. These will be considered or classified or categorized as oxyacids. Organic acids, none of the organic acids are considered strong acid. All of them are weak acids. Example for those ones, acetic acid. Okay, and we looked at that one earlier. Those are really good candidates for questions during the exam. So please try to read these carefully. Try to understand the Arrhenius definitions for acids and how we categorize the binary acids, the oxyacid, the organic acids, the polyprotic, diprotic, monoprotic, so on and so forth. Okay. Let's continue with acids, and now let's get into naming acids. Okay. First, when it comes to the binary acids, it is named as follows. First, you will use the hydro, which is the root name plus the root name of the halogen, and then ICE at the end. For example, if you look at HCl, so we use hydro, always hydro. So the name for the binary acids always starts with a hydro, and then the name of the halogen or the root of the halogen, and then you add IC acid. Okay, so example for this one is hydrochloric acid. Same thing with HF. So this one is hydrofluoric acid. And the same thing applies to all the halogens in the periodic table. Okay, so hydroionic acid, hydrobromic acid, so on and so forth, like HBr, hydrobromic acid. So that's when it comes to the binary acids. That's how we name the binary acids. So if you get a question to name HI or HBr or HCl, this is the rule that you should follow. When it comes to the oxyacids, if enough H plus ions are added to the root 8, and when we say root 8, we're talking about something like the nitrate, the sulfate, the phosphate. So if there was enough hydrogen ions or protons added in a way to neutralize or to completely neutralize the charge of the acid, then the root ATE will change to IC. So instead of nitrate, we'll call it nitric. And instead of sulfate, we'll call it sulfuric. And instead of phosphate, we'll call it phosphoric. So on and so forth. Okay. I'll give you an example. If you look at HNO3, which we have it right here on the slide, the root of the polyatomic ion, which is NO3 negative. This one is a nitrate polyatomic ion. I think we have talked about nitrate so many times at this point. I believe all of you guys should memorize the formula, the molecular formula, as well as the name at this point, okay? So nitrate, when you add the proton or the hydrogen cation, the H plus, to this in a way that neutralizes the total charge of the molecular or the compound, or the acidic compound, because the negative here is going to cancel out, the positive will cancel out with the negative, and HNO3 will be neutralized. So in this case, the nitrate will switch and will drop the ATE and will have IC at the end instead. Instead. So this one we call it nitric acid. Okay? Same thing, same deal with H2SO4. So SO4, the sulfate, okay, that's the name of this polyatomic ion. If you're adding 2H plus to make it H2SO4, the total charge over the H2SO4, it's neutralized. There is no charge over the H2SO4. Okay, so in this case, the ATE will be dropped and replaced with IC. So we call it sulfuric acid. Same thing with the phosphate. We call it phosphoric acid. Okay, so that's in terms of names and nomenclatures for the acids. So let's wrap up all the names and all the tips that we've learned so far when it comes to nomenclatures between bonds and also acids. So this chart right here that you're looking at, this basically summarizes the covalent bonding and the ionic bonding nomenclature, the acid nomenclature as well. So what you're looking at right here, this is simply two chapters almost combined together. Okay, so when it comes, let's go through it together. When it comes to type of compounds, if you're looking at binary covalent, and when we say binary covalent, that means non-metal to non-metal bond, and this is the generic formula for this. And when we say non-metal, something like CO2, correct? This is from the non-metal group on the periodic table. The name will be the prefix, unless if it's a mono, we don't use a mono. The name, the first element in the formula, like in this case, carbon, and then the prefix, you write the prefix, and then the name, and then the name of the element, and then you add IDE at the end. Okay, so in this case, carbon, di, because we need to indicate the subscript of the second atom here, which is the oxygen, so it will be carbon dioxide. Same thing with the N2O5. So you have dinitrogen, because we need to specify if it's a single nitrogen or if it's a single carbon, like in this one. We don't say mono to the first element, if you remember. Okay, but if it's more than a mono, if it's a di or tri, we'll have to specify that. So it's a dinitrogen, penta, because I have 5 of the oxygen, and it's pentaox, and IDE is added to the root. So that's when it comes to the binary covalent. Let's look at the next one, which is binary ionic. So the binary ionic is when you have a metal, which means someone from group 1 or group 2 in the periodic table, bonding to a non-metal. And in this case, you have cation and anion. This is the generic formula for this. Something like NaCl will be considered ionic compound, because chlorine is from the halogens in the periodic table, non-metals. Sodium is a metal from group 1 in the periodic table. Same thing with magnesium chloride. Okay? So when it comes to binary ionic, it is different from the covalent. You'll have to write the name of the metal. Okay? So just the name of the metal. And then you write the root of the non-metal, and then ID at the end. So with the binary ionic compound, we don't really specify the number of the non-metal. So we don't say dichloride, for example, for the magnesium. So we just say magnesium chloride. Okay? Same thing with sodium chloride. So that's when it comes to the binary ionic. When it comes to the binary with polyatomic ions, that's the formula. where X is the formula of the polyatomic ion, something like NaSO4. What you need to do is you'll need to write the name of the metal, which is sodium, okay, and then the name of the polyatomic ion, and that's relatively easy. So it's sodium, and the name of the polyatomic ion is sodium sulfate, okay, and there should be a 2 down here. Um, let's now dig into the acids. The acids, we have two categories that we have to focus on, which is either the binary acids or the oxyacids. If it's the binary acid, you'll use hydro, which is it refers to the hydrogen that you have here, plus the root of the nonmetal, either chlorine or bromine, and then you add IC acid. So there should be an IC here. Okay, hydrochloric acid, hydrofluoric acid, so on and so forth. When it comes to the oxyacid, you'll have to use the root of the acid plus IC acid. So you call it nitric acid, sulfuric acid, phosphoric acid, so on and so forth. So that's when it comes to naming acids. That's when it comes to categories for acids and how we can identify weak acids from strong acids. So let's now talk about bases and the characteristics of bases. So first and foremost, a base will have a bitter taste. Unlike the acid, which has a sour taste, the base will have a bitter taste. Okay, the base will also turn the color of a litmus paper from red to blue. So if you were to make a solution of sodium hydroxide and water, and you dip the litmus paper into your solution, you will see the color changes almost immediately from red to blue. If you remember, the acids were from blue to red, so the color would change from blue to red. Okay, the base would also feel slippery in your hand, so that slippery feeling that you get when you wash your hand with a soap bar, that's basically coming from a base, because the soaps are generally made from a basic component and also a fat component to basically make the cleaning work. So that first slippery feeling that you get when you wash your hand with a soap bar, that's basically the base. So that's how the base would feel if you were to touch it in your hand. Base also reacts with acids to form salts, and that's something we also mentioned when we talked about acids earlier. In terms of categorizing bases and classifying them, bases are classified either by type or by strength. Back in acids, we also had something as the number of protons. So the number of protons was another way to classify acids. We don't have such a thing when it comes to bases. So bases are classified either by type or by strength. When it comes to type of bases, we have three different types. First, we have the we have the metal hydroxide, and when we say metal hydroxide, that means any element from the group 1 and group 2 in the periodic table associated or bonded to a hydroxide ion. So some things such as an AOH, that would be a metal hydroxide. Something like KOH will also be considered a metal hydroxide. Calcium hydroxide will also be considered a metal hydroxide, so on and so forth. You get the idea, okay? So this is the first type of bases. The second one is the ionic compounds that containing carbonate or hydrogen carbonate. These will also be considered bases, and I will explain to you why in a second when we go through the chemical reaction. So that's number 1. This is number 2. And number 3 is ammonia. So ammonia is also considered a base, and that's due to the formation of hydroxide ions in a reaction with water, and we'll also look at the equation in a second. So these are the three main types of bases that I expect you to be familiar with. Okay, let's now see what Arrhenius definition is for bases. So when we looked at the acid definition, Arrhenius acid definition, it was any substance that forms the protons or H plus or hydronium when dissolved or when added to water. When it comes to the base, it's the hydroxide ion. Okay, That what determines if this material is a basic material or not a basic material. If the material forms OH ions, okay, or the hydroxide ion, when added to water, then that material is considered a basic material, regardless if that substance does have OH within its components or within its molecular structure or not. As long as it forms OH, hydroxide ions, it is considered a basic material. A basic solution generally is considered when you have hydroxide ions. Okay, so the highest the concentration of hydroxide ion, the more basic the solution will be, and vice versa. Okay, so a basic solution is considered when there's a significant concentration of hydroxide ions. So a strong base is basically the same logic here. Strong base, due to the completion reaction with water, it generates close to one or more hydroxide ion for each formula unit of the base added to water, something like NaOH. So the same idea when we talked about HCl, remember, same thing here applies with NaOH. So if I start with 10 NaOH in the beginning of my reaction, by the time the reaction is all completed, I will have 10 Na cations and I'll have 10 OH hydroxide ions. Okay, so the dissociation is complete dissociation of the hydrogen of the sodium hydroxide, and the reaction favors one side only, which is from the reactants to the product. There is no reversible reaction. So this one is considered a strong base. Okay. A weak base, on the other hand, is when you have a reversible reaction, just like when we looked at, for example, the acetic acid, right? If you remember the acetic acid, there was a reaction that points also back to the reactants, and that's due to the instability of the cation that is getting formed, or the anion at that point. Okay, the weak base here, same idea. Due to the reversible reaction with water, generates significantly less than 1 OH for each formula unit when added to water. So if you add if you add carbonate, for example, to water, the number of hydroxide ions formed are very small and very minimal. It barely changes the color for the litmus paper. Okay, so there's a hydroxide ion being formed, but when we look at this sodium hydroxide, for example, which is 100% dissociation, when it comes to the CO3 or the HCO3, the generation of the OH ions is very small. It can probably range from 1 to 2%. Okay? So that's why the hydrogen carbonate and the carbonate is considered weak bases, because the concentration of the hydroxide ion generated is very low. Now, ammonia is kind of like a different, along with the hydrogen carbonate and the carbonate, which we will look at in a second. Ammonia is a little bit of a different animal when it comes to acid, when it comes to bases. When we look at the metal hydroxide, they all contain OH ions within their molecular structure. So if you look at NaOH, there is OH right here, so it would make sense that the OH will be in a part of our products, correct? Same thing with KOH. I have OH in my molecular formula, so evidently OH will be part of my products when a dissociation reaction take place. But when you look at NH3, which is ammonia, I don't see any OH in ammonia. However, I still get OH as part of my products. And that's where ammonia becomes a little bit different when it comes to forming the hydroxide ions. So ammonia reacts with water in a reversible reaction, which forms ammonium and hydroxide ions. So it is a reversible reaction. That's the key word here. That means ammonia is a weak base because it's a reversible reaction. So what in fact happens when you add ammonia to water, as you see here, the ammonia will grab the proton of the water molecule. So this proton that will come off the water molecule, remember the water molecule looks like this, H, O, H. And we have two of the non-bonding pair of electrons. So what the ammonia does, it basically grabs this proton. And when this proton leaves the two electrons behind, okay? So now I have NH3 plus that proton that was taken from the water molecule plus OH with a negative charge. And that's basically what's happening in this equation right here. You have the ammonia reacting with water. The ammonia is grabbing that proton from water, which is resulting in ammonium with an M. That's why this one, NH4 plus. Okay, this is just for the sake of illustration. We don't really write it this way. So it's NH4 plus the hydroxide ions, and that's where the hydroxide comes from. So although ammonia does not have hydroxide by itself as an ion within its structure as NH3, but it still forms OH ions, which makes it classified as a basic material. However, the concentration of the OH formed in this case is a very small concentration. It's not a significant concentration. That's why it is indicated as a reversible reaction. It points back to the reactants. That's why ammonia is considered a weak base. Okay. That's basically just a quick drawing about how this all unfold, and you can see the ammonium right here. And this is the hydroxide ions, and you can see the hydroxide ions is in a very small amount compared to the ammonia right here. So you can see the ammonium concentration along with the hydroxide concentration right here. It is very insignificant compared to the ammonia concentration, which remains as ammonia molecule in water. Okay, but it's still, with that being said, due to the small generation, the small amount of OH, the low concentration of the OH ions are being formed, this is still considered as a basic material. Same kind of deal when it comes to the carbonate and the hydrogen carbonate. So for the carbonate, CO3, when it reacts with water, the carbonate will grab the proton of the water molecule. So if you have CO3, 2 negative, and you have O, that's H, you have the two non-bonding pair, the carbonate will grab the hydrogen ion, okay, which is the H plus of the water molecule, which would result in a hydroxide ion along with HCO3, 1 negative, I'm sorry, not 2 negative. Remember, when you add the proton, it's no longer 2 negative because the proton has a positive charge. So my negative charge here will drop by 1 figure. So now it is a negative charge at CO3. Okay, so the carbonate, same kind of logic here. Because the carbonate does not have OH within a structure, that does not mean it's not a basic molecule. It is still a basic molecule because it forms hydroxide ions, okay? But still, it is considered as a weak base because the concentration of the hydroxide ion formed is very low. As a result, we indicate that with a reversible reaction, pointing also to the reaction of the product of the reactants, because the hydrogen carbonate that is formed here is very unstable and it tends to drop that proton again, give it back to water. Okay, but it's still, there is some concentration of the hydroxide ion. That's why it is considered a base. Same thing with a hydrogen carbonate. Okay, so when it comes to Arrhenius base, let's do the summary here. We have either ionic compounds. When it comes to ionic compounds, that means it's the metal hydroxide. Okay, and those are all considered strong bases. Metal hydroxide, NaOH, and CaOH. 2. So this is a group 1 in the periodic table. This is a group 2 in the periodic table. So these metals will form will bond to the hydroxide to form bases that are strong bases. Okay. Certain uncharged molecules, there is none. Okay. only that is none as strong, okay, because it's only ammonia that is considered uncharged molecules, okay, that we recognize as base, and ammonia is considered a weak base. Something I missed here when it comes to the weak base, ionic compounds can form a weak base, ionic compounds with with the HCO3, which is hydrogen carbonate or carbonate. And when we say this, something like Na2CO3 or NaHCO3, both when reacted with water will form OH. Ammonia will form hydroxide ions. Okay? So that's when it comes to the strong base, when it comes to weak and strong, and also the classification of ionic compounds and also uncharged molecules like NH3. So when it comes to the pH scale measures the acidity and the basicity of solutions or substances in general. Pure water is considered a neutral substance or neutral solution. So the pH would be around the seven mark on the pH scale. Okay, acidic solution would have a pH value that is less than 7. So from 7 down below to 1 or 0, that would be more basic. More acidic. A basic solution would be between 7 and 14. Okay, so the closer you are to the value of 14, the more basic the solution. Okay, so something, for example, like NaOH, which is considered a strong base, will probably be between the 13 and the 14 mark, just because it's considered a strong base. On the other hand, when we're talking about strong bases, something like HNO3 or HCl, the hydrochloric acid or the nitric acid, so those folks would normally be in the 1 and 2 range of the pH. Okay, so the more acidic the solution, the lower the pH value. So for example, if we say a pH for a specific acid solution is 3, and compared to another solution that has a pH of 4, which one would be more acidic? pH 3 would be more acidic. Okay, and if you remember when we talked about acid dissociation and acid solutions in water, a higher acidity, the more acidic the solution, the higher the concentration of the hydronium ion, right? So pH 3 would have more concentration of the hydronium ion than a pH 3 solution. Okay, I'm pretty sure if you were taking any chemistry courses in the future, they would probably dig even deeper and show you how to even calculate the concentration for the hydronium ion using the pH scale. What I would like you to know at this point that the pH ranges between 0 and 14, 7 up to 14, that's basic region, 7 and below, that is the acidic region. That's the only thing that I would like you to focus on at this point, okay? The other thing probably that would be interesting to learn by looking at the pH scale, that between every mark and the one adjacent to it, there is a tenfold increase in a concentration for the hydronium ion. Okay, so if you're looking at 2 to 3, for example, as I said earlier, T2 would be more acidic. There is a tenfold increase in concentration of the hydronium ion in 2 compared to 3. Okay, so let's say hypothetically that you added a solution that you're looking at an acidic solution that has 10 counts of hydronium ion. Again, this is just for the sake of example of hydronium ion. 2 would have 10 folds more, so 10 times 10. Okay, so 2, the acidic solution at a pH of 2 would have 100 hydronium ion. Okay, so that's something just to keep in mind. That's in terms of the pH scale. Let's talk about neutralization reactions. So neutralization reactions is the type of reaction that happens and takes place between acids and bases, either a strong acid or weak acid, weak base or strong base. Anytime an acid and a base combine together, a neutralization reaction happens all the time. The byproduct of a neutralization reaction, or the products of a neutralization reaction, is always salt and water. Okay, there are cases where different where carbon dioxide is also formed. We will look at those just limited, maybe one or two examples, but generally, water is always formed in neutralization reaction. So when you're trying to put down the products of neutralization reaction, first thing you should write down in your product side is the H2O, because H2O always is part of the products for the neutralization reaction. What happens is essentially with the neutralization reaction, when we mix the acid and the base together, they basically counteract each other. When we are talking about the acids form the hydronium ion, correct? And what does the base form? The base form hydroxide ion. So the hydroxide ion, along with the hydronium ion, they would react with each other to form water. Okay, and they both cancel each other out. So not the acid is now dominating anymore, and not the base is now dominating anymore. The acid and the base, they cancel each other out, which brings the solution to a level where it's neutral. It has been neutralized. So it's no longer a 1 or 2, and it's no longer a 14 or 15. It goes down and drops down to the region of 7, probably maybe 8. So the solution is now doesn't have any acid or base properties anymore, because the hydronium ion and the OH has been taken care of by each other. Okay. So neutralization reaction. These are probably one of the things that I think all of us have tried to take advantage of in our daily life. If you have any acid reflux, you'll take one of those pills that basically neutralizes the acidity in your stomach. So if there's a high concentration of acid, what you're taking basically, you're ingesting the base, not a strong base, of course, because that would be harmful, but you are injecting an acceptable level of a base to neutralize the acid that it's been created in your stomach, so you can neutralize the medium in your stomach, so you no longer have that acid reflux. Okay. Um, when it comes to strong acid and strong base reaction, what happens basically, as we said here, we have the H3O, which is coming from the acid, and we have the OH, which is coming, oh, sorry, which is coming from the base. The product of the H3O and the H2O and the OH will be H2O or 2H2O. Now, the reason why we add a coefficient of 2 here, because we need to make sure that our equation is stoichiometrically balanced, okay? So we started with 3 and 4H. We'll have to end up with 4H. We started with 1, 2O. We'll have to finish with 2O, just to always keep that in mind. So the hydronium ion, the H3O, from the strong acid, reacts with the hydroxide, the OH, from the strong base to form water. So we have the hydronium ion, which is the H3O. Um, uh, we have the O, H, H. We have 3 H's. And we have the positive charge for this one. And we have the OH, the hydroxide. Okay. With the non-bonding pair around the oxygen. So what happens, and this one has a negative charge. Oh, come on. This has a negative charge. So this hydrogen here, because it's very unstable, will leave this hydronium ion, will come and bond with this oxygen on the hydroxide. And instead of having a hydronium ion with 3 hydrogen and an OH with short of 1 hydrogen, you will have OH, oops, you'll have OH, you have 2 non-bonding pair, and you will have another H2O. And that's the reason why we have 2 H2O in our equation as well. Because 1 HO3 with one hydroxide will give away two water molecules. Okay? So that's what happens when a strong acid and a strong base react together, and basically a neutralization reaction take place. And this is how water is formed. So how does the solution, how does the reaction actually unfold in a solution of water when you have HNO3 and you add NaOH to that medium or to that solution? So what happens, as you see here, you will have the OH, just like how we mentioned earlier. You will have the reaction of OH and H3O to form water. Okay, you have the sodium ions and the nitrate ions, which is coming from NaOH, and that's where the OH is coming from. Okay, and you have the HNO3, and that's where the hydronium is coming from, and this is where the nitrate ion is coming from. So you have NO3 negative, and you have the sodium cations also coming from the NaOH. So those guys, the sodium cation and the nitrate anion, they will remain in solution, not involved at all in the formation of water. For that reason, we call both the sodium cation and the nitrate anion as spectator ions. And this term should really ring a bell with you, right? Because we did talk about spectator ions back in the precipitation reaction. And the role for those ions back in precipitation reaction, basically just like the role of the sodium and the nitrate in this case, just watching a reaction unfold without really intervening or getting involved at all. Okay, so the sodium cation and the nitrate anions, these are considered spectator ions because they are not involved in the formation of water or the neutralization reaction. A neutralization reaction is also considered a double displacement because you have two partners that are changing partners. Okay, so if you're looking at the cations and anions, they will both switch partners. You have A pairs with D, and C will pair with B in this case. And this is very similar to the precipitation reaction. It's only in this case we're talking about acid bases and we're not talking about salts. So that's your that's your indication when it comes to acid, when it comes to neutralization reaction versus precipitation reaction. Neutralization reactions involve acids and bases, and you should be able to tell just right from looking at the molecular structure if we're talking about an acid, we're talking about base, while precipitation reaction, we're talking about salts. Okay, so neutralization reaction with a hydroxide base, example is HNO3 with NaOH. First thing first, we'll have to label our A, B, C, and D. So for example, if we start with AB, which is the nitric acid, my A will be the hydrogen ion, my B will be the nitrate, C will be the sodium, and D will be the hydroxide ion. Okay? Product is always water. So the product are water and ionic compound. So water is always a common element in neutralization reaction, and then you will have an ionic compound formed as well. Something like NaNO3, right? NaNO3 is an ionic compound because sodium is from group 1 in the periodic table. Writing a neutralization reaction. Well, so here you are at the exam, or you're trying to do any practice problems, and you have an acid and base reacting together, and I'm asking you to write the products for this neutralization reaction. Well, here's how you can do it. First, you'll have to determine the charge of ions, which is A, B, and C. So you'll have to determine the identity as well as the charge for these ions. Well, how do I determine the charge of these cations and anions? First, the periodic table is a good resource. Second, you can always look at the molecular structure or the compound, and you can figure out the charges of the cations and anions through the examples that we did before. Okay, then once you identify the identity as well as the charge of A, B, C, and D, then you'll have to do the double displacement reaction. So A and D and C and B will now forming new bonds. Okay, now something to keep in mind that when you form new compounds, the net charge over these compounds is always 0. Okay, and what that means that when you're doing the CMB and forming the new bonds, you make sure that the oxidation number for the A, B, C, and D are being taken into consideration to make sure that your total charge over the compound is always zero. Okay, then you determine the states of A and D, your products or new products, and C and B as well. Generally, they are in aqueous. Okay, and I don't really expect many of them to be solids. In neutralization reaction, a lot of times they are in aqueous state, but you can always refer to the solubility table for that. Okay, your product, as I said earlier many times at this point, it's always water, and an ionic compound. Okay, so let's take the first example. Now this one is HCl with KOH, a strong acid and a strong base. Now we're calling the hydrogen chloride as a monoprotic acid, and that's because I have only one hydrogen. If I were to have two hydrogens or three hydrogen, the name would be different. So first thing, what I will do is I'll have to identify my A, B, C, and D along with the charges. So first, my A, B. All right, let's make some room. Oops. So first, let's determine A, B, C, and D. My A is hydrogen, and hydrogen has a positive charge. Chlorine is a negative charge. It's part of the halogens on the periodic table, and it always has a negative, one negative charge above, right? If you are out of luck and you really can't remember all these from the periodic table, if hydrogen is a positive one, then chlorine has to be a negative one. So the positive can cancel the negative, and that's why we have a neutral HCl molecule. Okay, let's look now at our C, which is potassium. Okay, now potassium from the periodic table is a group 1, so it always has a positive 1 charge. Okay, so again, if you can't remember that group 1 in the periodic table has a positive 1 oxidation number all the time, then I would assume that all of you remembers and knows at this point that hydroxide, OH, is always a single negative charge. So if I have a single negative charge and I have a neutral molecule for the KOH, meaning there's no charge, there's zero charge above the KOH, that means potassium has to be a positive one in order to cancel this one negative of the hydroxide. Okay, so there's multiple ways that you can tell what is the charge over these cations and anions. Hydroxide is a single negative. So now I have identified my A, B, C, and D. Now let's do the double displacement. So now B is going to bond with C, and A and D will form a new bond. So my products would look like this. A and D, that would look HOH. But I can write this one as H2O. Now, in the exam, if you would like to write it as HOH, although I prefer that you write it as H2O, but if you do and write it as HOH, I'll still take this one and I will not deduct any points. Okay, so I don't want you to be concerned about that one. So my next thing that I have here, my next product is B and C bonding together, and that would be KCl. Oops. That would be KCl. Now, I have identified my product. I have identified my A, B, C, and D, the charges. Now I got to my products. Now I'll have to identify the physical state for each of them. So H2O, obviously, it is a liquid, so it's always an L. If you look at KCl, K is from group 1 in the periodic table, and based on the solubility charge, KCl will be an aqueous substance. Okay? So it will be soluble in water. This basically conclude your neutralization reaction. So if I were to ask you to write a neutralization reaction for hydrogen chloride and KOH, that's how you would do. This is how you would do it. Okay? Let's do, I think we have at least a couple more examples. Okay, let's take now a polyprotic acid with a hydroxide base. So when we say a polyprotic, that means I have multiple protons that forms from the dissociation of this acid. And in this case, we're talking about H2SO4. And as we all know at this point, that H2SO4 has two protons. So that's why it's considered a polyprotic acid. Okay, so let's go back to the neutralization reaction because that's essentially what we're trying to do here. So when we're trying to do something like this, you'll have to stick to the basics. So what that means, you'll have to identify your A, B, C, and D along with their charges. So let's do that together. So let's do our A, B, C, and D. So when it comes to my A in my reactant, which is the H2SO4, that is the proton. The B, that will be the sulfate, which is the SO4 2 negative. Okay, the 2 negative here, you can figure that out from multiple ways. First, from the polyatomic ions table that we went over multiple times. Or you can also look at the H2SO4 molecule overall because we know the proton is always a positive charge. And since I have two of this, that means I must have two negative charge to counteract to this two positive charge. So the SO4 must be two negative. Okay, so if you can't memorize the polyatomic ion table, you should be able at least to do the math in this case. All right, so let's do the C now. So my C now is the sodium cation, which is a positive charge, group 1 in the periodic table. OH hydroxide, it's a negative. So now I have my A, B, C, and D along with their charges. What I can do now, I can do now the double displacement. So A will be with D and B will be with C. So my products would look like this. H2O, as always, that always forms, plus I have Na plus and SO4 2 negative. Now when I try to write this molecular structure, what I need to do, I need to do the swapping, right, of charges in order to write the correct molecular structure. So this will be Na2SO4. Okay? Now, as you may notice here, that this equation is not balanced, right? Because I have 2 Na and I have 1 Na in here. So what I will do is I'll have to make sure that my equation is stoichiometrically balanced. So what I'll have to do is add a 2 in here to make sure that the sodium has been balanced. So now you can double check your math and make sure that everything, all the count of atoms on the products equal the count of atoms on the reactants, and that's the case. I'll let you do that on your own. Okay. So now I have my products already. The equation is balanced. Next thing I need to do is I need to write down the physical state of all the products that I have here. So for the H2O, that will be a liquid. For the Na2SO4, that would be an aqueous because of group 1 in the periodic table, sodium. Okay? So that's when it comes to something like a polyprotic acid reacting with a base. Another polyprotic acid that's also kind of interesting to do the neutralization reaction is the H3PO4. And that will be an extra credit. So you can try that on your own and bring that to the lab, the day that you listen to this lecture or the same week. Okay, so the neutralization reaction of carbonate, and if you remember when we talked about carbonate and their acidic or their basic behavior, we said although they don't have OH within their molecular structure, they do form OH, and we went over their dissociation equation. So carbonate, when they react with an acid, this will be an acid-base reaction, and that's where people gets confused all the time when they see an acid, something like HCl, and carbonate, like sodium carbonate. They will think of this as a precipitation reaction, and that's not the case because sodium carbonate will behave as a base in this case. Okay. Um, same kind of steps, which is identifying your A, B, C, and D along with their charges. The products all the time is water, along with carbon dioxide and NaCl, the salt, as an aqueous. Okay. So the product of reacting with carbonate is water, carbon dioxide, and an ionic compound. When I say sodium carbonate or carbonate in general, that also apply to something like okay, NaHCO3. This will also behave as a base if you react that with something like HCl. Okay, so that could be a neutralization reaction. So do not confuse that and think of this as a precipitation reaction. So that's in terms of carbonate. So that's for the neutralization reaction. Now let's talk about Bronsted-Lowry acid and base. So we talked about Arrhenius acid, and that's basically what we have all been going through when it comes to acids and base. And we at this point, I think it's been well established that for Arrhenius, an acid is a solution that forms, or a material or substance that forms hydronium ion or generates H3 positive ions when added to water. The base, when it generates OH or hydroxide ions when it's added to water. Bronsted and Lowry, they came with another definition. It's not about the hydronium ion, it's not about the hydroxide, it's about the proton H and being a donor or being an acceptor to that proton. So an acid would be a donor for that proton. The base would be an acceptor for that proton. So it doesn't necessarily mean that you're forming an OH. It doesn't really necessarily mean that the substance is forming a hydronium ion. It's about the proton donation and the proton accepting substance. So the Arrhenius definition has its own pros and cons. One of the positive aspects of the Arrhenius definition that you can isolate substances and identify substances based on the formation of the hydronium ion or based on the formation of the hydroxide ion. It also allows to prediction whether the substance will react with an acid or would react with a base based on either if it is forming hydronium ion or forming hydroxide. The Arrhenius definition for acid also helps us determine the pH of solution, either if it is above or below 7. But on the other hand, one of the shortcomings of the Arrhenius definition that it really fails to explain reactions when it comes to hydrogen transfer. So a reaction that does not involve hydronium formation, it does not involve hydroxide formation, but it only involves hydrogen ion transfer between the products. The Arrhenius definition does not really and cannot really explain these kind of reactions. The Bronsted-Lowry, on the other hand, it includes similar reaction that basically involves the transfer of hydrogen, the transfer of hydrogen ion, and we can explain these as acid and base reaction. On the other hand, the negative aspects of Bronsted-Lowry definition, it cannot really isolate substances based on the formation of hydrogen, of hydronium ion or the hydroxide ion, and also it cannot really explain and cannot really predict if this material would react with an acid or a base, and it cannot really determine or evaluate the pH solution of the substance if it is more than or less than 7. That's in terms of Bronsted-Lowry. A new term that I would like you to be familiar with is the conjugate acid-base pair. And again, here we are focusing on the proton transfer. So although you may see something like hydroxide in this equation, but this is not our center of attention. What we are focusing on at this point, we're focusing on the transfer of protons. Okay, so if I have a reaction of ammonia, for example, reacting with water, we are tracing the proton, and we would like to see where this proton is going and where this proton is coming from. Because where it's coming from, that would be my proton donor, aka the acid. where the proton is going to, that would be the proton acceptor, or also known as the base. Okay. Um, the proton donor will have its conjugate, so which is the acid, will have its conjugate base on the products, on the product side, and the proton acceptor, which is the base, will have its conjugate acid on the other, on the product side. The conjugate base and the conjugate acid, that's if you were to add the proton one more time to the conjugate base, you would form the acid back in the reactant, to the reactant side. We will look at examples in a second. And the conjugate base is basically vice versa. Okay? So back to the ammonia reaction with water. If you notice here, the proton is transferred from water to the ammonia. Well, how can I tell this? Because ammonia here, the NH3 is no longer an ammonia, it is now an H4. So an additional hydrogen atom has been added, and the ammonia has changed. The total charge for the molecule has changed to a positive. So we can tell a hydrogen proton has been added. Okay, so the fact that the ammonia has accepted the proton, that will evidently make the water as the hydrogen ion donate. Okay, or donor. And that would make the ammonia as the acceptor. Okay, the ammonia is the acceptor, so ammonia will be considered the base, which would make the ammonium the conjugate acid. Because the reason why we call it the conjugate acid, because this ammonium, if it loses the proton, it will go back to the original ammonia. So the ammonia and the ammonium will be considered a conjugate acid, conjugate acid base pair. Okay? Same thing with the water. The water is the donor for the hydrogen. Okay? If I look at the OH here, this will be the conjugate base for the acid water on the reactant side, because if I add the proton back into the hydroxide, it will form the original water molecule on the reactant side. So the OH and the H2O, this is acid base conjugate pair. Okay? All right, let's look at some examples of Bronsted-Lowry proton donating, and proton accepting, and how we can label our conjugate acid, conjugate base, and acid and base conjugate pair. Okay, let's look at the first one here. So we have ammonia reacting with hydrogen fluoride to form NH4 and fluoride ions. So first, again, we're not focusing on hydroxide. We're not focusing on the formation of hydronium ion. We are literally just looking for the proton, and we would like to trace where that proton is going and where that proton is coming from. So if I look at the ammonia here, I can tell that the ammonia has gained a proton. And I can see here the hydrogen fluoride lost the proton, and the reason for that, you can see the fluoride anion without the proton. So the proton is no longer associated with the hydrogen fluoride. So that would make the hydrogen fluoride the acid based on Bronsted-Lowry definition, right? So this would make it the acid because it's the donor. And that would, of course, make the fluoride the base, or the conjugate base, I should say. Okay? Now let's look at the ammonia. The ammonia has gained a proton, so it is the proton acceptor. So the ammonia is the base, the ammonium is the conjugate, acid. Because if I lose the proton, if the ammonium loses the proton, the additional proton will form the ammonia back in the reactants, right? And that's why we have the reversible reaction, because this reaction goes to the products, to the reactant on both ways. Okay? So if I were to ask what is the can you name a conjugate acid, an acid-base conjugate pair? So the NH3 and the NH4 plus. This is conjugate acid base pair. Okay? And same thing for the hydrogen fluoride and the fluoride. Let's look at the next one, which is water reacting with hydrogen fluoride. So again, we are trying to trace the proton. Every time you see boron acid Lowry, forget about the acid, forget about the hydronium and the hydroxide, and we're focusing on the proton. So we're tracing the proton to see where that proton is going. So first thing I can see the hydrogen fluoride no longer have the hydrogen atom, correct? Or the hydrogen ion. Rather, it is now with the fluoride only. So I can tell that the hydrogen fluoride lost the proton, so that makes the hydrogen fluoride the acid. Because it's the donor, it donated that proton. The water, on the other hand, this will make it the base. Oh, let's do it color coding. So this is the base. Okay, this makes the H3O the conjugate acid. Makes the fluoride the conjugate base. Because if the proton goes back to the fluoride, it will form the acid back to the reactants. Okay, so the fluoride and the hydrogen fluoride are acid-base conjugate pair. Let's look at the ammonia and water. Okay, so the ammonia and water, we can see here the ammonia gained the proton, and the water lost the proton. Correct. So that makes the ammonia gain the proton. So it's the acceptor. So it's a base. That would make the water the acid because it's the donor. The ammonium is now it's the acid, or it's the conjugate acid. And the hydroxide is now the conjugate base. Making some spaghetti lines in here. Running out of space. Okay, let's look at our last example here. Hydrogen phosphate and hydrogen fluoride. Okay, so at a first glance, you will say, okay, so those both are acids based on Arrhenius reaction or Arrhenius definition, right? Both of these materials, if you were to apply Arrhenius definition for acid and base, the definition would not really be able to explain which one will be the acid, which one will be the base. Bronsted and Lowry can explain and can identify which substance is the acid and which substance is the base based on the proton donating and a proton accepting. So when I look at the hydrogen phosphate, I can see the hydrogen phosphate accepted a proton, right? It increased the number of hydrogens in here. So the hydrogen phosphate will be the base. And this will be the conjugate acid. Let's look at the hydrogen fluoride. Hydrogen fluoride is the acid. This will be the conjugate. Conjugate base. So this is how we identify the acid and the base based on the Bronsted-Lowry definition. Yes, you will have a question on a Bronsted-Lowry acid and base um, identification on the exam. So I'll give you a couple of questions, few equations probably, and ask you to identify which one is the acid, which one is the base, following Bronsted-Lowry definition. Now, according to Bronsted-Lowry definition of proton donating and proton accepting, some substances can behave as an acid and behave as a base in the same time, depending on the type of material or type of substance that it's reacting with. So, that's what we call amphoteric substances. So, when a compound acts in a Bronsted-Lowry acid in one reaction and behaves as a base in another reaction, that's what we call it an amphoteric substances. And there's some examples. So first, the first one that you're looking at is the hydrogen carbonate reacting with hydrogen fluoride. So what we need to find first is we need to find our acid and we need to find our base. Um, Again, it might be a little bit hard to tell here, like especially on the hydrogen carbonate, to see if it is an proton acceptor or proton donator, but it's pretty easy for the hydrogen fluoride because we can see fluoride here has lost the proton or the hydrogen that it started with in the reactant side. Okay, so this would make the hydrogen fluoride the acid, and this one will be the conjugate base. Okay, and by process of elimination, this makes the hydrogen carbonate the base, and this will make it both the conjugate acid. You can consider the water and the carbon dioxide is the acid. So that's in terms of the hydrogen carbonate in reaction number one. Let's look at reaction number two. Hydrogen carbonate reacting with the hydroxide. And we can see here the hydrogen carbonate has lost the proton or the hydrogen that it started with in the reactant side. So we can say at this point, based on the Bronsted-Lowry definition, that the hydrogen carbonate in reaction number two is the acid because it is the proton donator. It had donated the proton. And this will make it the conjugate base. On the other hand, you can look at the hydroxide. The hydroxide accepted that that proton from the hydrogen carbonate. So this will be the base, or it is the base by just process of elimination. Okay, so if this one is the base, the water will be the conjugate acid. Oops, the conjugate acid. Let's look at another example. So we can see here that the HCO3 reacted as an acid or as a base in the first example, in the first equation, and HCO3 reacted as an acid in reaction number two. So we can consider the hydrogen carbonate as amphoteric substance. Okay. Let's look at our last example of this unit, which is the hydrogen phosphate. The hydrogen phosphate reacting with hydrogen fluoride, and we can see the hydrogen fluoride lost the proton because the fluoride now is no longer associated with that hydrogen. So we can make the hydrogen fluoride as the acid. This will make the fluoride the conjugate base. Okay? If you look at the hydrogen phosphate, it accepted that proton, right? The number of hydrogen has increased. So this will make it the base, and this will be the conjugated acid. So hydrogen phosphate reacting as a base in reaction number three. In reaction number four, it is reacting with hydroxide, and we can see here the proton or the hydrogens are no longer associated with the phosphate. In fact, the phosphate is now sitting by itself. So the hydrogen phosphate is the proton donator. It donated these protons, so this make it the acid, unlike the first reaction, which was the base. This, by a process of elimination, will make the OH the base. Since this is the acid, this will be the conjugate base for the acid, the hydrogen phosphate, and this will be the conjugate acid. Okay? So that's in terms of the amphoteric substances. I think at this point, this covers everything in Unit 6. And if you guys, as always, if you guys have any questions, shoot me an email, try to do the practice problems, and I'll be available if you have any questions. Okay?